Okay, so Blake got it to where T, what was your decimal? 10 point,
I think I found a closer one.
okay, 77.
Here, 10.77313921.
Okay, and getting it pretty darn close to 350,000. Now, granted, I am not going to require you to go to that extreme when we are trying to predict, to estimate something, okay? But it does get a little addicting on the exponents as you try to get it as close as you possibly can. In our next sections, we're going to be talking about logarithms and natural logs, and that's where we could actually algebraically solve this exactly using that. But right now, before we get to that, we're going to be using guess and check via the table, via a graph, and via just algebraically plugging in some numbers, okay? So this is done very similar to to the population that we had yesterday, okay? All right, now, River City, example down below. Population of River City in the year 1910 was 4,200. Assume the population increased at a rate of 2.25% per year. Estimate the population in 1930 and 1945, and then we'll estimate when the population will reach 20,000. Now, this is again similar to what we did yesterday, except what's the difference? What's the wording? What's the difference in the wording? What do we see here that we haven't seen before? Okay, we're going to estimate the population. What's the other word that we're seeing? The what? We're seeing a rate now. We're seeing a rate. Up until now, we've had a growth factor, or we've had to figure out what the growth factor is. But in this example, we're seeing a rate. That's where this may not come across as you're sitting there taking these notes like, oh, not a big deal. But when you start throwing it all together and differentiating between a growth factor versus what the rate is and how to apply it and plug it back into our function, be very careful with that. So this is my rate. So what I'm looking at here is, and this is population, I'm looking at this. No different than y equals a times b to the x. Please understand that. Absolutely no difference. Except for the fact we're going to use a population. We're going to take the growth factor. We're going to take that factor and break it into our 1 plus our rate when the rate is given, or when I need to figure out what the rate is. All right, so what's my initial population? When they first started counting, or when they first started gathering data for this particular study. Okay, so that is my P sub 0. That's my initial population. So 4,200. And so what I have here is 2.25%. How do I write that as a decimal?
0.0225.
Move it over twice, 0.0225. So I put that in for my rate, 0.0225 at some time. And so combining that, bless you, I get 4,200 times 1.0225 raised to the t power. That's the function I'm going to use to answer these questions. So now I want to estimate the population in 1930. Am I going to actually use 1910 and 1930 using those numbers? No, they're dates. Those are years. So I know that 1910 is actually time 0. Time 0. So if I want to estimate in 1930, what's my time? 20. And how do we get 20? 30 minus 10. So from 1910 to 1930, 20 years passed. So I will plug that into my handy-dandy population formula. And about how many people were in River City in the year 1930. Perfect. 6,554 people. And obviously we can't put it as 0.1 because we don't have partial people. This example came directly out of your textbook. And so know that this is going to be very similar to what you will see on your homework as well. So let's do the same thing to 1945. But what's going to change? T. And what's T in 1945? You guys got it. And again, that's the time that has passed from the initial time that it started collecting data to 1945. 9,150 people.
When it's like people, do you always have to round down? Because if it's like 0.9, and we
You still can't have a. Then is somebody missing an arm
Well, I don't know, but like.
or a leg or?
You never had 9,000 people probably, more than likely.
Typically, yes. You just truncate it off. Okay? So again, now we want to predict when the population will reach 20,000, doing the same that we've been doing. Somebody tell me an approximate how many years will it take to reach 20,000? Use your method of choice. About how many? Okay, AJ says about 71 years. To reach 20,000. So is that growing very fast? No, but at least it's growing. And again, this would be assuming a constant growth rate. Okay, this would be assuming a constant growth rate as we go through. Okay, questions so far on population. And the main thing that you need to worry about here is, or I shouldn't say worry about, but pay close attention, be detail oriented with, is as you read through the problem, are you looking for a growth factor, decay factor? Are you looking for a rate? Is the factor given? Is the rate given? And how I apply that into my basic exponential function. Okay, so paying close attention to pulling those different pieces out. Okay, we're going to transition now into the logistic function. This is something that we're not as familiar with as we are with some of the other graphs that we've seen and different formulas that we've seen. Back in chapter 1, might have been the beginning of chapter 2, we looked at parent functions. There were 12 parent functions. Logistic function was one of them. And the one thing you need to understand with logistic function, if you remember the shape of it, it started out having a limit. There was like a horizontal asymptote coming off from negative infinity, going up, and then approaching another horizontal asymptote going off to positive infinity. Okay, and when I say going off to positive, I don't mean up and down, I mean east and west. Okay, another horizontal asymptote. So, and in that particular function, it was a horizontal asymptote at 0. As x approaches negative infinity, we had a horizontal asymptote approaching 1 at positive infinity as x approaches positive infinity. Okay? What that means is that with the logistic function is used when there is a maximum sustained population, a maximum sustained something. And I look at us in this room. There is a maximum height that a person can grow to. And I'm not going to say it's 7 foot. I'm not going to say it's 8 foot. Heck, you know, there might be somebody over in, and actually I think it's Russia, Sweden, Turkey, somebody like that, that, you know, super 9 something. Actually, I totally just made that up. But whoever the tallest person is.
It's like 8 to 10.
So it's 8'10"?
I think it's 8 to 10.
Okay. So let's say 9, let's just be safe and let's say 9 feet. That in our culture, that there is nobody that will grow over 9 feet tall. That is a maximum sustainable height. Trees don't grow to infinity. It's not Jack and the Beanstalk time, you know, where it just continues to grow and grow and grow. Trees even have a maximum height at which they grow, depending upon the species of the tree. State parks have a maximum sustainable population of some of the animals that they have in their state parks. They can only have X number of bears, or things might get overrun. There's a maximum sustainable population of deer. Otherwise, other things, the ecosystem doesn't work right, or they just run out of space because a state park has a finite area that these animals have to roam and to play and frolic and have fun. That's when a logistic function is used, when there's a maximum that you can reach, okay? So you look at this, and this is the basic function. And I still like to throw out a gimme. Now sometimes my gimmies aren't gimmies to you, but they're gimmies to me as far as on the quiz. Oh, everybody will get this one right, okay? So here's your gimme for the next quiz. If I ask you, what is the maximum sustainable population of coyotes in the St. Louis Zoo, okay? And you're given a logistic function, and it's on there, and it's 10 over 1 plus something, something, something. Guess what your answer will be? 10. That C stands for whatever that maximum sustainable population is. You literally just pull that number out, and that is your maximum sustainable population in a logistic function. So that states it can't be more than that, okay? Now A, we still have our initial, but we've got a little bit different situation in which with the logistic function, we're going to talk about that here in a second. And now we're going to our E, our base E, raised to the negative K. K is a constant that will be given for you. And then actually E to the K is our base, is our growth factor or decay factor. And then X is still our time or whatever amount of whatever we're looking for, okay? So let's apply this now to this situation. We have New York City, 20th century U.S. data. The population of New York State can be modeled by this logistic function here, where P is the population in millions. Okay, so whatever number's given, then multiply it by a million. And T is the number of years since 1800. Okay, no, I was not alive in 1800. Some of you might think that, but I can't even relate to this one. The 1990, I got you on. The 1800s, not there. Based on this model, what was the population of New York in 1850? Okay, we'll work through that here in a second. What was the initial population? We'll work through that here in a second. And what is New York's maximum sustainable population? The limit to growth. That last question is your gimme. What is that? 19,875, but remember, that's in millions. New York State has a maximum population that it can, if you think about it, yeah, every state should have, you know, for the produce and everything and the infrastructure and everything that it has. Yes, there is a maximum amount that it can hold, so to speak. All right, so this last one is an easy one, so we'll just put 19. And that's in millions. So, or you could just put 6 zeros right behind it. Okay. So I want to know, let's go back to the first question then. There's your gimme. I want to go back to the first question. Based on this model, what was the population of New York in 1850? This is just like what we've done before. What am I going to do? This is going to be 50 years since 1800. That's when it started. So I'm going to, on my calculator, I know it's going to be awful. It actually won't be that bad. Make sure you include your parentheses down below in the denominator. T gets replaced with 50. So in the year 1850, T is going to be 50. So by plugging that in, and don't forget you're using E to the X power, which is the one right above the LN button. And you can check my work on that. I got about 1.97. And that's negative 0.035005, and then times 50. Okay? We good with that? Again, making sure that we have parentheses around that denominator will be the key, and otherwise, then it's just plugging in your values. And the time is being multiplied by that exponent. Time is still in the exponent. So also make sure that you haven't gotten out of the exponent if you're not coming up with the correct answer. Make sure that the time is there. Did you get that, Pamela? Okay. All right, so now that is what was the population in 1850. What is the initial population? This is where we're going to differ and take just a little bit different route than what we did in our basic y equals a times b to the x, being able to pull that out. With the logistic function, we have our a, where we got 57, starting value there. But if I want to find the initial value using my logistic function, what time is my initial value? I'm sorry, yes. At what time do I find my initial value? When x is what? When x is 0. Okay, when x is 0. So basically, in your basic function, let me see if I can explain this to you. When x is 0, look at this. I need all your eyes up here so you can see why I'm not just pulling a out. When x is 0 in my basic function, anything raised to the 0 power is always what? 1. So now I've got a times 1. So that's why that is going to be my initial value. When x is 0, that's why it's always going to be a. But if I do that down here, I've got a whole bunch of other stuff going on, so I can't just pull out my a. But I'm going to do this exactly the same way. When x is 0, and in this case, when time is 0, I'm still going to find my initial value. It's just not going to be as simple as pulling this out. So stay with me. And you can, trust me, you can do this without a calculator. Okay? 0. If t is 0, what's 0 times all of that? 0. Okay? So my exponent now is just 0. What's e to the 0 power? 1. What's 1 times 57,993? What's 57,993 plus 1?
I was thinking decimal.
Okay, so I kind of lied. You do have to now pull out a calculator. So now I'm going to take 19,875 divided by 57,994. And I do think a lot of your problems are such that if you would take the numerator divided by the denominator, you could do it in your head. Like this is 100 divided by 50. So the answer is 2. And so, and I'm just going to write this out for you so that you can see where that's coming from. And you should get approximately,
0.34.
and remember, it's in millions.